Okay, everybody, welcome to the UEI Technical Masterclass. I'm Bob Finn with UEI, and I hope everyone here is doing well this morning. Today's webinar is entitled Application Architecture, Key Points to Using Handles, Device Numbers, Processes, Threads, and Data Acquisition Modes Successfully in Your Application. Our co-presenters today will be our own Timur Raza and Phil Zavitas. In this masterclass, Timur and Phil will provide tips and tricks to ensure a strong application architecture. As I say every week, I want to remind you, all our webinar attendees, that this is an interactive environment and we encourage all of you to ask questions. So if you've got a question, send it our way using the webinar chat tool. That about wraps up the introduction. So without further ado, I'm going to turn the webinar over to you, Timur.
Thanks, Bob. All right. So I think this photo right here would be a good place to start. This is an image of the new Summit supercomputer at Oak Ridge National Labs. And I chose this because I thought it would be kind of a good, nice, striking visual way to think about performance computing and how we can get the best performance out of all the cores, the threads, the processes, and the other system resources we might have available to us at any given time. However, we don't all have access to supercomputers. A lot of the time, we'll be trying to implement our algorithms that are tough and involve control and learning and so on our edge computing devices, right? Our UEI packs, our control PCs in, control cabinets, with our Power DNA racks and so on. So I think that's kind of a good place to start in terms of talking about how do we get the best performance and how do we take advantage of concepts such as interrupts and threads and processes for our applications. So today, here's our table of contents. We'll be talking about obtaining handles to the I/O module in certain ways, right? If we've got multiple threads running, right? Multiple processes. We'll talk about how to address each I/O board. And then we'll move into a kind of a discussion of really good practices in terms of kind of the most granular part of each one of our boards, right? Or each one of our chassis. In short, how do we bind computing resources to hardware resources in a way that makes a lot of sense and that is both fast and efficient. All right, so I've kind of mentioned the three big concepts we'll be talking about today, but I figured I would do it a little bit more formally. So the three technologies / concepts that we'll be talking about are events, processes, and threads. We use events so that we can avoid constantly polling, right? If we have a trigger on a digital board, for example, right, that might be an area where a separate event that we can just kind of offload would be very useful. It prevents our main computing and execution threads from being bogged down by polls. And of course, events can be different, right? They can be messages from a 1553 board or a message to a serial port or so on. Now, the next thing we will cover today are processes, right? If we want to control many different IOMs or run many different programs at the same time, we want to leverage our OS capabilities, right? That's where we would use processes, right? And the final concept that we'll be covering today are threads. In this case, we'd have a single process and likely be very well organized and structured, maybe use one thread to control the whole IOM while use another thread to write data from that IOM, for example, to file, or use different threads to control different parts of the IOM. In short, how do we organize the different computing resources, right? The hardware computing resources that we have to take advantage of inputs, outputs, file writes, communication, and so on. All right, so let's start with our IOM handles discussion. So our first example is pretty easy. We've all done this. If we want to open a connection to an IOM in a single process, right? For example, with Visual Studio or through the Bash terminal or anything else, we would use the DQ open IOM function. And in this, we would pass a blank handle. The IOM would then take this handle, fill it in, and then respond to this handle whenever it was queried. So this way we've got kind of a link between that process and that IOM. And then in that case, once we have this handle prepared, we can use it for all sorts of things, such as a DQ ADV 207 read, or to set up channels on a VMAP, or to set scan rates for particular boards, or to set channel lists, and so on. But again, this is pretty basic. If you're here, you've probably done most of the stuff already. So let's make it a little bit more difficult. If we want to talk to multiple IOMs from a single process, we can do that too. But again, we would just follow the same process that we followed for one IOM. You would use DQ open IOM and pass differently named blank handles to each of the IOMs. And that way you've got a single process controlling many different IOMs. But of course, you might be thinking, all right, if I can have one process controlling many different IOMs, maybe it would be more efficient to use multiple processes to control multiple IOMs. Getting a little bit ahead of myself here. You would, in order to actually access and work with the different IOMs, you would again simply expand on how you did it with one process, with one IOM. You'd use VMAP, add channel, you'd set scan rates, set channel lists independently for each of the IOMs. All right, here. All right, so I'd mentioned maybe it's more efficient to use multiple processes or multiple threads to access different IOMs. After all, you've got more than one thread, right? You paid for the entire CPU. Maybe you should get to use the entire CPU to maximize performance in this case. So in this case, each additional application or process in this case would need a new handle from DQ open IOM. However, if you were using different event threads or DAC threads, you'd need to use DQ add IOM port so that the IOM would recognize that it's getting requests from a specific thread or needs to address a specific asynchronous event in its own thread, which is different from addressing a specific CPU or a general execution thread. Okay, so let's jump back to the kind of example diagram, right? In this case, we've got three different processes. The first process we've seen before. We use DQ open IOM, and because it's in the main execution thread, you simply pass the handle in and everything is good. In process number two, the goal would be to control the IOM with a thread that we spawn later on. So here we need to use DQ open IOM and DQ add IOM port, right? So the add IOM port ensures that the thread and the IOM communicate seamlessly. And then in process number three, we do two different things. We set up both a control thread and an asynchronous event thread. So we would need to use DQ add IOM port once for the control thread, and then again for the asynchronous event thread. And that way we can now take advantage of many more resources on board our application, which should help us operate much more efficiently. All right, so on to part two, which is device numbers. And this part, again, I think is more of an overview so that we set up for our best practices section, so that we all have a setup for our best practices section. So I took this slide from earlier on where I showed the usage of a handle. But as you can see, we also need to pass in a device number to that given process. So we bind specific processes and specific threads to specific I/O boards, right? And this is advantageous because if we have a lot of I/O boards on our chassis, we're using a DNR12, for example, we might not want to address every single thing with one thread, right? That would be an inefficient way to go about it, I think. So with the cube, device numbers are pretty easy. From top to bottom, they're numbered from 0 onwards. The largest cube we have, I believe, is a 7 slot. So DEVN 0 through 6. However, with racks, it's a little bit more difficult. Right, so here we've got a completely full DNR12 example rack. And here I've annotated how there's a little bit of a difference between the slot number and the device number. The slot numbers are fixed. They're the physical hardware location of that particular I/O board. The device number is simply if a board exists there, counting up from left to right. So in a completely full rack, we go from device number 0 through device number 11. However, if you didn't fill in a DNR12 completely, the device numbers would automatically switch such that you still counted up for every board that was in the rack. So first one's device number 0, second one's 1, and so on. Doesn't matter where in the rack they are, they could all be on the right side. You could have them interspersed. They would still count up automatically. Now, we might be thinking, all right, that's kind of interesting, but what if I don't have access to my physical device? What if I need a more dynamic way of figuring out what exactly is in this chassis, right? Maybe it's in some other part of the building. Maybe we have multiple chassis in different parts of the building and they're not configured identically. We can dynamically figure out what devices are in which chassis, right? Whether it's a cube or a rack or so on. So this first method uses a struct that we automatically pass back every time you use DQ open IOM, the DQRD CFG struct. Now this struct contains an array of every single device, right? Using both the dev mod, which would be the device model, and the option in case you have a board such as the 308-350, right? So this way you can automatically query everything on board the chassis and have your program dynamically address what is there. All right, now there's actually another way to do it, and this way is really only useful with the Power DNR chassis, the rack chassis. This is the DQ get DEVN by slot function. The idea is that you pass in the handle and the handle and the slot number, and it will fill in the device number, the serial number, the address and the model of whatever device happens to be in that physical slot. All right, so now that I've kind of laid the groundwork, my fellow applications engineer, Phil Zavitas, will take you through a crash course on our best practices on binding threads and processes, on using DAC modes, and using Ethernet ports with your own computing hardware to get the best possible performance that you can. Phil, take it away.
Thanks, Timur. Hi, everyone. We'll start with a little bit of overview of what processes and threads do and are. You can consider a process a program. So if we envision Microsoft Word launching, that might be considered the process, and Word has functionality to it. So it might be spell checking, auto-saving, printing. And so that process or application might separate functionality into threads. This allows the code to be readable, and it also allows the system to assign priority to what's going on within those threads. So some design considerations: processes protect their memory from other processes. So a program will be separate from another program. the threads within a process actually share memory. So it might be easier to have threads that need access to the same data do the work versus separate processes. There's also a longer switch time between processes than between threads. So these are just operating system concepts to consider when you're architecting your application. The work in a process can be done without threads, or the process can spawn 2 threads or 3 threads. Sorry. The thread, again, is designed to compartmentalize functionality, but it's also designed to allow the OS to run what's most important when necessary, something called priorities. So the OS can assign, your application can assign a priority to thread 1 being the most important, thread 2 next, and thread 3 last. When thread 1 is ready to run, the operating system will stop everything and allow thread 1 to run. When it's done, it will go to the next highest priority thread ready to run. So these concepts are all here for your use, and there are design considerations on how you want to architect your application. And we just want to talk about how this relates to our equipment. Another example is send and receive. You may have a send thread, a receive thread, and within there is functionality that may or may not be assigned to separate threads. Data acquisition modes. We have several data acquisition modes, and I'm not going to detail each one. I just want to give a high-level description. Point by point and RTDMap are designed to get single points per channel. They do it a little differently. That's why there's 2 modes. But you get a single data point per channel. VMAP and ACB give you multiple data points per channel. And that's the difference. We'll talk about how to use those within a system. We also have Ethernet ports, and there's 2 Ethernet ports in the system. So we'll talk about guidelines for usage. So here are some rules and guidelines to consider. 1 PC on 1 Ethernet to control the I/O boards. Our system is designed to have 1 PC on 1 port controlling the I/O boards. You can have 20 PCs networked in for failover reasons, but during application execution, we're asking that 1 PC on 1 port be used, and it doesn't matter what port. You could also fail over to the other port. We're also asking that a maximum of 1 process per I/O board. So please don't have 2 processes trying to access the same I/O board. The system was not designed for that purpose. And also a maximum of 1 data acquisition mode per I/O board. So threads, these are some guidelines. If you have I/O boards that are running in similar rates, you may want to run them in the same thread. If you have I/O boards at different rates or different types of I/O boards, you may want to have a dedicated thread per rate or port type. And then if you have a messaging I/O board, maybe it has 4 CAN ports, and each CAN port is running at a different rate, then you could have a dedicated thread per port if you wish. These are not requirements, but these are guidelines to streamline your application. So if we take a look here, what we're trying to avoid is 2 control threads on 1 I/O board, 2 data acquisition modes or 2 processes on 1 I/O board. And again, avoiding having 2 PCs trying to control the I/O boards. We separate things out, and we have 1 thread, control thread per I/O board. We have 1 PC controlling the I/O boards, but you can have a second PC running diagnostics or a second Ethernet port on the first PC. And we have sample code that will show you how to get diagnostic information on the CPU and the I/O boards while you're using the system. Processes are separated out. And again, if you have multiple ports at different rates, you could run individual threads. So you could have one process for all I/O boards. You could have a process for 6 and 6. You can separate it out as 2, 2, and one process for the rest. It's totally up to what your application goals are. So we're starting to develop an application note. I know this is a lot of words here. I'm not going to read them all. It's a summation of what everything's been said. You call Open IOM initially, and then when you need threads for asynchronous events or control, you're going to get an additional handle. The Ethernet ports, just use one process per I/O board maximum, one data acquisition mode per I/O board, and then some guidelines to running the threads. Applications are all unique. We would like to work with you on yours, discuss different architectures, and help you get started with the best approach. So we're all here, ready to help. If you'd like to reach out when you want to talk about your application architecture, you can email us or give us a call. Let's take a look at any questions that have come in. Okay, if I have a cube in hosted mode, is there a way to implement a failover system if there was a network loss or the PC went down? Yes, we have had people that deployed multiple PCs and there would be some sort of handshaking going on, and if the initial control PC went down, it would fail over to the second PC. It would simply restart the application. That also went for the Ethernet ports as well. Can I have RTDMap running in one thread and VMAP in another? Absolutely. You can have, you just need to call add IOM port to get a unique handle for each thread, and then do the appropriate setup code to use the two different modes. What if someone removed an I/O board before I start the application? Well, Timur had pointed out some ways to auto-detect the I/O boards, and we do recommend that you check the system at startup. If for some reason one is removed and the device numbers are hard-coded into the application, you will most likely get a -12 error, which is a bad DEVN. I hope this has been helpful, and seriously, reach out. We're here, and we'd be glad to help get your application architected.
Okay, I think I'm going to hop back in here, Phil. So this about concludes today's presentation. A few things to note. We are shifting our schedule from bi-weekly to monthly. So our next masterclass will be October 29th, which means it's just in time for Halloween. This particular session will focus on iRig applications. We record every webinar and post the videos online. You can find these archived masterclass videos on our YouTube page or on our own webpage, ueidaq.com/videos. And finally, if you've got questions, need additional support, or you've got a suggestion for a future webinar topic, please email us at support@ueidaq.com or give us a call, 508-921-4600. As always, we hope you found today's webinar useful, and we'll see you again in October. Once again, thank you for joining us, and enjoy the fall, and if you can, please stay healthy.